Here's a problem where we calculate the moment around a point using the scalar method. Typically we use the scalar method in a two-dimensional Cartesian system. It's not limited to the scalar system in 2D, but it's generally a little bit easier. So our formula for this problem is going to be the magnitude of a moment around a point is equal to the force times the moment arm, or the perpendicular distance. It's pretty straightforward, but sometimes when your force vector either is at an angle, it can be a little confusing to how to incorporate the angle with the distance. So below here we have a couple conceptual examples. So we have a force that's hitting the beam at this angle. Here's our origin point. So the thing I like to do is I like to draw my x and y components going in the same direction that this force vector is hitting that point. So my y component is going to go down this way, and then my x component would typically come in this way. But since it's in line with the origin point, it's really not that necessary for this problem. So when you first calculate your a moment around a point, you need to make a prediction of which way you think that the object will rotate around the point. So this is typically counterclockwise, usually the standard. So now that we have this y component drawn here, we just imagine that there's a y component from this origin point, and then this would be our distance. So this is the perpendicular distance from this y component to the origin point. Now, since this y component is pushing down in the same direction as this force vector, the calculation will end up being a negative value because it's spinning clockwise, while we had initial standard set for it to be counterclockwise. So the way this plays out is since this theta angle is touching the x-axis, we know that for this distance we need to use sine theta, because there's no angle given here touching on our y component. So how we would calculate this out, since this is going in the down direction, it'd be negative f sine theta times our distance. And that'll give us a moment around this point here. Now for this example, as you see, the origin point is in a higher part of the beam, so you know that this x component is going to play a value for the distance. So same thing, I like to draw my x and y components going in the same direction as my force vector. So my y component is going to go this way, my x component is going to go this way. Since this is pulling on the beam, the y component is going to be a negative value because it's going to pull the beam down. Since this is pulling out, this will typically cause it to rotate counterclockwise, so it'll be a positive value. So we're going to put our prediction here. And then once again, we just have a hypothetical perpendicular wall here from the origin point. And this would be distance 1 from our y component. And this could be distance 2 for our x component. So since our theta angle here is touching the x-axis, we'll go ahead and have and it's going to be a positive value since it's causing it to rotate counterclockwise. We'll have f cosine theta times d2, and then we'll just subtract it by, since this y component is pulling the beam down to go clockwise, we'll subtract it by f sine theta times d1. That'll give us our moment around this origin point here. So we're going to use these same concepts for our example problem here. The one thing about this problem, it's a little unique. It's actually asking which way the pole will rotate. There's two opposite forces, so you kind of have to calculate which force is being exerted in a higher amount. So it's a hypothetical situation where two guys are pulling on a rope here. So once again, we're going to just kind of predict that this pole is going to rotate counterclockwise. And then, as you can see here, our origin point is A, and then the rope starts at the in the middle of the pole, in line with point A. So what this tells us is that our y component isn't necessary for these calculations because there's going to be no perpendicular distance. For example, if I were just to draw a line here, like it's perfectly in line with A, so like we wouldn't be able to calculate that distance. So we don't have to worry about our x values. So we'll go ahead and just draw our x components. So it's going to go the same, point in the same direction as our ropes. So I'm going to draw this one out here, and then just have this arrow going. And this is a 45, 45, 90 triangle. You'll know that this is 45 degrees right here. Now we'll do the same thing here. We'll just have this x component going the same way as our force vector down there. Now, since we want to know the individual moments of each force around this point A, we'll have to do it one at a time. So let's go ahead and just start with force P here. And once again, we predict that we'll have a counterclockwise rotation. Now, if you take a look at this x component, it's going to be pulling this pole this way, which will cause it to rotate around point A in a counterclockwise direction. So our value will be a positive value here. So we'll have the moment of P around point A, and that's going to be equal to, so we have a force value of 40, and we have an angle value of 45 degrees, and it's touching the x-axis. So you know that that's going to be cosine 45. So we have our force value, 40. And then we just need to multiply by the distance. So the total distance of this pole to point A is 22 feet. So multiply that by 22. And that gives us a value of 622 foot per pound, going in the counterclockwise direction. Since we're calculating using two different distances with both force and, two different units using force and distance, that needs to be incorporated in our final answer. So it'd be 622 feet per pound. So for the moment of F around A, once again we'll predict counterclockwise rotation. Now if you look at this x value here, it's going out this way. It's probably going to cause this beam to rotate in the clockwise direction, almost like if you were to consider it being stationary on A. So that means this is going to be a negative value. So since we have a triangle here, I'm just going to go ahead and use the x component and divide it by the hypotenuse to calculate my angle difference. So for this, it's going to be 4/5. It's going to be a negative value times 60. And our distance from this point to point A is 14 feet. So multiply that by 14, and we get a value of negative 672 feet per pound, going in the counterclockwise direction. So what that means, it's actually going 672 feet per pound in the clockwise direction. So now we have to compare these two values. So we have 622 going counterclockwise, and we have 672 going clockwise. So obviously the clockwise direction is larger, so this pole is rotating clockwise. So yeah, it's pretty straightforward. Just when it comes to these scalar moment problems, especially in 2D, just uh, just just analyze it and try and draw your x and y components, and that can kind of give you an idea of how it's gonna rotate around the point, and it'll give you that perfect perpendicular distance that you can calculate, or how to use your angle, since this x component here is touching our angle. We know that's going to be cosine 45, so there's no confusion there.